we got Michael recording. We're all set. Okay. All right. So anyway, so we're talking about nutrition, metabolism, and body temperature stuff. So nutrition actually has a series of terms in there. When you talk about a kilocalorie, a kcal is actually a defined unit. It is the amount of heat energy required to raise the mass of something of water 1 degree Celsius. Okay, so 1 kilogram of water, 1 degree Celsius. So it really has meaning. When you look at the essential daily requirements and stuff and how many calories are in something that you eat, just so you know, in America, we'll put like, it's 240 calories for this particular, I'm making sure I don't have anybody who's in waiting, but when you read, it's 240 calories for your, what you're eating, it's really 240,000 calories. If you go to a non-America place, you'll see it in the hundreds of thousands and you'll go, oh my God. It's because we don't like to put kcals because it hurts people's feelings. All right. Okay. And Michael, I'm going to have to rely on you. I'm trying to make sure I can see the waiting room, but I can't. So I don't want anybody sitting out there. So that would be bad, but it's not showing me anybody popping in. So I'm hoping everybody's here. All right. So anyway, so a nutrient is actually something in the food used by your body that we need in order to allow for normal growth, maintenance, and repair. So nutrients. And nutrients are things that you would expect, like how much carbohydrate, protein, lipid, water, vitamins, minerals. These are our major nutrients. Essential nutrients are the ones that we actually cannot manufacture from other nutrients. So you have to get in your diet. So when you hear about an essential nutrient, it means you must eat it, okay? Or else get it in the veins if you are someone who can't eat anything. So a lot of our nutrients actually, through the magic of our all hail the liver, all hail the liver, we can manufacture an awful lot of stuff by using what we're going to look at, the Krebs cycle. We can kind of spin in and spin out of our nutrient pools. It's really absolutely amazing. It's like this magic thing, a carousel. You jump on it one way and you come off the other way. It's cool. So when we talk about our nutrients, the stuff that's on this plate is showing you how much you should have of each. They used to have a pyramid where you'd have like, the top of the pyramid was a tiny little triangle of fats and, down at the base you'd have your carbs. But I don't know about you, I don't eat that way. So I eat more on a plate. So when they finally came up with this much better representation, it gives you kind of an idea of how much of your plate should be each of the different things. So carbohydrates, you need to know that glucose is the monosaccharide of the realm, okay? There are other monosaccharides like fructose and galactose, but they are going to be converted to glucose in order for us to use them. So your key monosaccharide for our use in the world of metabolism is glucose. And we've got the primary source, of course, is plants, right? I mean, I don't know about you, but I wouldn't look at a steak and say, oh, well, it's got glycogen stored in there, so I'm going to look at that as a carb source. No, we look at plants. And they talk about simple carbs versus complex carbs. So the simple carbs are like the monosaccharides and the disaccharides. For instance, your table sugar, sucrose, is a disaccharide. It's glucose plus fructose. The complex carbs are the polysaccharides. These are your starches, all right? The only animal carbohydrate that we would actually eat and say we have carbs in it is the lactose. For people who are lactose intolerant, for instance, one of the things that you can do is you can actually look at your cheese and see what the carb content is, because the really aged cheeses, they've broken down all of the lactose. So people who have lactose intolerance can actually have some of those harder cheeses like the Parmesans and the hard, sharp cheddars and things like that. You just look at the label and it says, it has 0 carbs. Then the lactose was all used up. The softer cheeses, like goat cheeses and stuff like that, they'll have a carb count. That's saying that there's still some lactose in it. But again, I wouldn't eat my cheese saying I'm eating cheese in order to get my carbs in. It's just not my primary source. It's plants. So the reason you need carbs, the primary reason for having carbs in our diet is that they are our readily available cash in our pockets or our underwear drawers. It is our primary energy source for the body. If you are an athlete who does things like triathlons or something, you're one of those that, does carb loading, they'll tell you what they'll do is load up on pasta and things like that before a meet because they want to load up with glycogen so that they have a readily available, basically a supply of energy, the cash in their pocket. You couldn't have your DNA and RNA without carbs because, remember the rungs of the ladder of DNA, those are deoxyribonucleic acids. Ribose is a sugar. It is a monosaccharide. Deoxyribose, ribose, so DNA, RNA, the whole side of the structure is actually a monosaccharide linked together. All right. We do have some that are stuck to our cell surface. We've got what we call the Glycocalyx. Back when you learned the cell, back in ANP1, you had the Glycocalyx. Part of it is for cell adhesions because, let's face it, sticky sugar coating, it'd make it sticky, so it makes sense. Okay. Proteins. Our proteins come in two different types. You've got your complete proteins and your incomplete proteins. What a complete protein is something that has all of the essential amino acids. Okay, so the easiest way to get complete proteins is to eat animal products. So that includes dairy. You don't have to kill the animal, but certainly when you eat striated skeletal muscle, or even if you like smooth muscle things like innards, you are getting complete proteins because you are getting all the essential amino acids that you need in order to survive, okay, in order to make all the proteins you need. Okay, so I'm switching over to here, and this shows you your essential amino acids. Now, the interesting thing is that with incomplete proteins, which are most all of our plant products, if you are going to look for proteins in plants, I bet one of the first things that you look for protein. What do people eat if they want protein in vegetables? Beans. Yes, exactly.
A magical fruit.
A magical fruit, yes, the more you eat. Nuts are great too, right? Get a handful of nuts. Nuts are a great source of protein. So are grains and vegetables. But the thing about them is that when you look at most of the plant products, they are incomplete proteins. And what that means is that they don't have enough of all of the essential amino acids. So, like one of the staples of diets in a lot of places is beans and rice, right? And that really comes from, if you think about it, it's brilliant because there's not much lysine in the grains, but beans have a lot of lysine. So when you eat your beans with your rice, then you're getting your essential amino acids, and nobody had to die. Okay. So anyway, if you know what you're doing, you can be a very, very healthy vegan. But if you don't know what you're doing, it could really be disastrous because you need to make sure you know what has what, so you don't lose something. Because your body can't say, well, you know what? They ate a whole lot of beans the other day, so let's just store up on the lysine in case beans don't come along in the diet for a number of weeks. Well, it doesn't work that way. You're going to take what you need, use what you need as lysine, and the rest of it, the lysine is going to be broken down and turned into something else. So we don't hold on to these things. You don't have like a storage spot for the amino acids. Okay. So the functions of proteins in your body, I think most people, if you ask them, well, what do you think protein's good for? It's kind of, you would think structural, right? Because there's an awful lot of structure to it. Your muscle, your connective tissue, your skin, all that stuff, it's protein, right? So certainly structure is a huge thing for proteins, but start going down the list of all the things that are proteins. Enzymes are proteins. We couldn't do anything without enzymes because even though enzymes can only lower activation energy and make it has to be a possible reaction, but it wouldn't occur fast enough for us to be able to be alive without enzymes facilitating everything. You also have hemoglobin, for instance, for transporting. So we use proteins to transport things. There are other examples like transferrin, these that carry iron. So transport is a big one. Hormones, oh my goodness, right? Epinephrine, norepinephrine. We couldn't have the adrenaline rush. You couldn't have growth hormone. There are so many hormones. Most of our hormones, remember, are amino acid based. So all of these things, proteins get a whole lot of different job description credit. So when we talk about proteins, remember the monomer unit of a protein is the amino acid. So the amino acids, there's this thing called an all or none rule. And what it basically means is that you must have all the essential amino acids in order to be okay. All right. So when you look at this slide here, which is your picture in your books over on page 929. 929. Yeah. 929. You can see that it shows you these essential amino acids, okay? And if you look at them, how many are there? 1, 2, 3, 4, 5, 6, 7, 8. That's it, out of 20. So these guys are essential amino acids. And your body can't say, well, you know, my messenger RNA instructions are that I really need to have a lysine in this spot. But you know what? Lysine, leucine, they sound pretty close. So let's just stick a leucine instead of a lysine. It won't work, right? So you must have the essential amino acids in order to be able to have everything you need in order to create your proteins, okay? We do not store amino acids just hoping someday that we'll call on them. Let's see, nitrogen balance. Nitrogen balance is about protein synthesis versus breakdown. So anabolic building versus catabolic breaking down, okay? So if you are in a positive nitrogen balance, that means that your protein synthesis, the anabolic reactions, exceed the catabolic, the breakdown reactions. This is going to be like kids, right? They're growing. You're constantly getting bigger. You're making new parts. Your growth hormone is very busy. So you are building, that's a positive nitrogen balance. If you are a pregnant female, you yourself are making another human. You are in a positive nitrogen balance. If you're not, it's not okay. Negative nitrogen balance is when you are in a state that's not good. Your protein breakdown exceeds your protein synthesis. So catabolic exceeds anabolic. So when you're sick, when you're injured, when you're stressed, and right now, honestly, there's a whole lot of stress around, right? A whole lot of stress. So, you know, I would wager that an awful lot of people in this country and on this planet, actually, because since this is really a pandemic going on, and life has really changed. I mean, you know, people are panicking over having toilet paper, for the love of God. So anyway, I would say that probably there are a lot of people who are in a negative nitrogen balance. So what we really want to be is in a nitrogen balance, neither positive nor negative, as long as we're an adult and we're just sort of staying our course. Anabolic hormones. So our anabolic hormones, of course, growth hormone would be the first thing that you would think of, right? Insulin is actually an anabolic hormone. Catabolic hormones are things like our glucocorticoids, right? So cortisone, cortisol, corticosterone, these are the things that are going to break down proteins for energy. We do gluconeogenesis. Remember that word? New glucose generated. Okay, so I did a little exercise a while back, and I figured out what my dietary requirements would be for proteins. So let me just, this was the easiest calculation thing. It's not that I would eat all this stuff, but hey. So at 0.8 grams per kilogram body weight, here's what I could have. I could have a peanut butter and jelly sandwich and a cup of milk for lunch. And then for dinner, I could have a cheeseburger and a milkshake. Notice I gave myself a milkshake and cheese. But That's not very much. I didn't give myself breakfast, did I? So Americans tend to want a lot of protein in their diet. It's not necessarily all that they need. They might be eating a little extra, in which case we take those amino acids and feed them into the let's make fat out of this. All righty? Okay, so next, lipids. Let's move on to my lipids. Let's move past here. Let's get down. I gotta scroll. Up, back one. Okay. All right, lipids. So this table, you know I love tables, right? So this table is over on page 930. Wonderful table. So lipids, we've got two sources of them, animal and plant. Saturated versus unsaturated fats. Anybody not heard of saturated versus unsaturated fats? Everybody good? Okay. Do you know where you get your saturated fats? Animals or plants?
Animals.
Yes. Okay, so animals, saturated fats, what that means is if you remember back to ANP1, this is where I would really like to have my board, plus you're missing my comics. Anyway, saturated fats, if everybody would go into their books and turn all the way back to the chemistry chapter, I know one of your total favorite chapters. And if you looked over on page, just before this one, move along. Oh, trying to find my fats. Got my proteins, need my fats. Here's my fats. Okay, if you look over on page 46 in your textbook, okay? Everybody got their textbook, right? That's part of the deal. So they've got saturated fat versus unsaturated fat. A saturated fat, what it means is that the glycerol backbone, which is that upright 3-carbon thing, is hooked to 3 fatty acid chains. And every single carbon on that fatty acid chain of each of those 3 is holding single bond hands. So what I want you to look at on page 46 is how nicely those fatty acid chains line up. They stack really well. They are like straight logs. So you could build a log home out of them, like telephone poles, okay? Now, the unsaturated fats, these are from plants. And unsaturated fats, what that means is that instead of just single bonds between each adjacent carbon, you have double bonds. And every time you get a double bond, you get a kink, okay? So they show you the single bond versus double bond on page 45. So if you kind of look backwards in time, there's single bonds, and they make a perfect little ziggy-zagging. And then the double bonds over on page 46 show you the kink. So here's the deal. If you want a solid fat at room temperature, having saturated fats where there are no kinks, they stack up really nicely like blocks, okay? So that's why if you put a piece of meat on the counter at room temperature, it doesn't liquefy on you. Plants are the oils, right? So the plants are the unsaturated fats, and those are better for you. You want the plants, the unsaturated, which have the double bonds. And every double bond, if you have a monounsaturated fat, that's one double bond, which means that there's one kink. If you're polyunsaturated, you have more than one double bond and there's more than one kink, which starts making it something that won't stack. So you've got liquids. So the the plant oils, those fats are oils. And we really do need to have fats. You can't skip any fat in your diet. So anybody who says, well, I'm just going to live on salads with no oil or anything, and I don't eat meat, and I'm going to have no fats, well, they're going to be in trouble because you need to have essential fatty acids. We do have essential fatty acids, linoleic acid, linolenic acid. There are essential fatty acids we absolutely must get in our diet. So you have to have some fat. And of course, we have lingual lipase to make it taste good. So we're highly motivated to eat some fats. Okay? Now, big thing about fats and their job description. their number one thing on their list is energy. Now we saw number one for carbs, but carbs are your cash in your pocket. They're readily available, okay? Because they clip off. When you take glycogen, you start clipping on all those different branched pieces. You get glucose molecules really fast. That is my energy molecule of my body. But with fats, they are much more bang for their buck. So the fat is a really high energy fuel. And the reason for it is, it'll become clear, but it's made up. So hold this into your thoughts for a minute. The fats have a whole lot of acetyl groups. So if you look at those fatty acid chains on page 45 or 44, and you see all those little zigzags, each pair of carbons gets to go through our catabolic machinery, through the Krebs cycle and the electron transport chain. It gets to go through once. Every time it goes through, it generates a lot of ATP. So when you start looking at the fatty acid chains and looking at how many little 2-carbon units we can get from that, you can see that we get a whole lot of energy from one fatty acid chain. There are 3 fatty acid chains in a neutral fat because they are called triglycerides. So you have a whole lot of energy store in fat. So it yields the highest amount of energy per gram when metabolized. That's a huge deal. It's why our body wants to make fat, because in the world of biology, we don't know when our next meal will come from. And it may be that you have plenty in your cupboards and in your refrigerator and your freezer, but your body doesn't get that. And biologically speaking, we're going to try and hold on to as much fat as we can. So we store it everywhere, right? That's how you get all that subcutaneous fat, and you get those cottage cheesy looking legs sometimes, and you've got the greater omentum loads up, and we store it on in those epiploic appendages all over, hanging on our colon. You've got it everywhere because the body says, I never know. It's like a hoarder, right? Because it's great long-term energy storage. It's just hard to get because I don't know if you've ever seen Finding Nemo, but it's like the adipocytes are like those gulls. They whine, 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 whine. So it's hard to get it out. If you've ever tried to lose weight, yeah, there you go. But it's great for high energy stuff. And then, of course, there are a lot of other things that are really important. For instance, we could not have a cell membrane if we didn't have lipids, because it's a phospholipid bilayer. We would all just be pouring into each other. Talk about lack of social distancing ability. I mean, we'd be these puddles that flowed together. It's like, I don't know where you begin and where I end. I don't know, it sounds like some romantic thing, but it would be really, really messy. So phospholipid bilayers of cell membranes, they're carriers. We're going to look at some of the lipid carrying things. We've got lipids are important. Remember, when I have a micelle coming into my cell in the small intestines, that's how I get my fat soluble vitamins, A, D, E, and K in. They can't come in if they don't have fat to carry them in, the micelles. And then they turn into the chylomicrons and travel around in the chyle through our lymphatic system until they dump into that subclavian vein, the left side. All right, then we've got just plain old adipose itself, right? That fat padding stuff, I don't know, if you land on your bum really hard, it's helpful if you've got some fat padding there instead of just landing right on your bony butt. If you live where it's cold, or you live with somebody who likes to turn the thermostat to low, it's helpful if you have the same amount of adipose to agree on what's comfortable, because adipose keeps you warmer, right? Skinny person with well-padded person, it's the battle of the thermostat. And then we also have cholesterol. So remember our steroid hormones like testosterone and our estrogen, progesterone, and aldosterone, those things, they're based on cholesterol. Cholesterol is a lipid. Cholesterol is just a multi-ringed lipid. You wouldn't have bile salts for emulsifying fats. The reason that it works is because bile is made from cholesterol. Those are the cholesterol salts. It's bile. It's why people, when they get gallstones, it's called cholecystitis. cholecystectomy because I'm taking out the gallbladder because it's filled with gallstones, right? Cholecystectomy. Okay. So anyway, so far so good. Everybody okay? A thumbs up here and there? Okay. All right, vitamins. Vitamins are really important as coenzymes. A coenzyme is something that helps an enzyme do its job, but it doesn't get used up in the reaction. So we're going to look at a couple of coenzymes, NAD and FADH, that they act as carriers. They're like taxi cabs in order to carry electrons and protons along in order to drop them off so that we can make ATP. So they carry energy, in essence, to our battery charging system and then go back and find some more to carry again. So they're like a taxi, they're recycled. Vitamins are important. You get them in a balanced diet. And this is where I always have to, I promised my father years ago, he's a biochemist, that I would tell everybody as I go through this part. So you will get your vitamins in a balanced diet. So unless you have some kind of an absorptive problem or some other kind of a pathology related to a vitamin insufficiency or an absorption issue, you should just get your vitamins in a balanced diet instead of buying all these vitamin pills. You can actually poison yourself if you get too much of the fat-soluble vitamins. And my example that I have is, I didn't see it. Well, I might have, but I don't remember. But when my mother was in the hospital having me, it was back in the day of wards. And yes, we actually had hospitals back then. It wasn't like out in tents in the middle of the desert. So, but there was a woman that was on the ward with her who was absolutely bright orange, she said. And what had happened was she had done the brilliant American thing of if some is good, more is better, most is bestest. And I don't know how anybody could eat that many carrots, but she had gotten herself into hypervitaminosis A, and she was not okay. And when we actually talk about the vitamins, there's a whole table. So each of the vitamins, it tells you what it's for, where it's from, and what happens if you have too much or too little. So any of the fat-soluble ones, you have to really watch out because you can end up with hypervitaminosis because the liver will store fat-soluble vitamins to toxic levels. It's a problem, okay? So be very careful if you take vitamins. The B vitamins, the C vitamins, those are water-soluble, so you'll just have expensive urine, but be careful. Vitamin B and K, those vitamins, our gut flora in the colon will make those. So they do make some of them. You can also eat some, okay? So everybody cool with fat soluble versus water soluble? Okay. I don't want to hear about anybody getting too much of vitamin E or something because they just thought poorly. All right, minerals. Now in your books, by the way, it's page 932 that has vitamins, and then minerals is on page 933. Let me see what I have over here because I've kind of been running my mouth instead of getting pictures up. There's the chart. Sorry about that. So there are the vitamins. And take a look at what happens if you have hypervitaminosis. Let's see, where is my A? There it is. Look at that. Too much, headache, irritability, vomiting, hair loss, blurred vision, liver and bone damage. All because you had too many carrots. So be careful. All right, minerals. Minerals, you need moderate amounts of some of them. They're key ones like sodium and potassium and calcium, chloride, magnesium, phosphorus, sulfur. These are things that you need moderate amounts of. There are others that they say you need in trace amounts. So things like iron, you don't need a lot of it, but you need enough for your hemoglobin. Iodine, you need it for, what do you need iodine for? Just curious.
The
thyroid. Exactly, the thyroid hormones, the thyroxine, triiodothyronine, right? So things like that, manganese, zinc, right? There are some things that you need in trace amounts. So if we look at some of these things, calcium, you know where to get it, right? Dairy products, but do you have to eat dairy in order to get your calcium? No. If you are a vegan, you just need to make sure you get enough kale and beans, things like that. Okay. So when you think about the different minerals that we have, like phosphorus, ATP, this is the energy coin of our realm, right? You've got to have phosphorus, those high energy phosphate groups in ATP. There are two high energy phosphate groups. For our fluid and electrolyte balance, we really, really rely on sodium, potassium, and chloride. Okay, remember the chloride shift with the respiratory system, and we had to get the chloride going back and forth so we could get the bicarbonate to go forth and back. They go opposites, right? And remember sodium and potassium, ATPase pump. We kick out 3 sodiums, we bring in 2 potassiums. All right, but what do you think is the highest amount, which mineral do we have the most of?
Calcium?
Yes. Why? You're right. Why?
Bones?
Yes. So calcium and phosphorus are by far and away, they're about 3/4 of our total simply because we use them to make our skeletal system, which is a huge chunk of our weight. Okay. Cool so far? All righty. Let's move on down. Okay. All right. So metabolism, there are terms, okay? And this is where in your course, I put some good links. Now, I don't generally try and put links in because they tend to die out or something, but there are some really good links to help with animation. There are some Khan Academy things that show you how things work in more depth, a little more depth than actually I require. And then there are ones that if you like songs that are actually fairly cute and still right, okay, still correct, but then those are at a lower detail than you actually have to know. But I strongly encourage you to start looking at some of the videos, okay? And I'm going to try and pull one up. We'll see how well it works because who knows? All right, I've put it up, but we'll see if it'll come up. All right, so processes of metabolism. Catabolism. Whenever we say catabolic, think catabolic. Okay, so catabolic, this is hydrolysis. This is hydrolysis. Remember where you insert water to break a bond. Okay, so cellular respiration, in the cell, we take glucose through a process called glycolysis to form something called pyruvic acid and acetyl-CoA. And then in the mitochondria, we're going to go through the Krebs cycle and through something called oxidative phosphorylation to form ATP. Okay, so this is what's coming up. And remember our deal that, you know, that pinky swear thing on day 1 when we were all together in a room. Hopefully you've taken a look at this and your brains didn't go, meow. All right, anabolic. What does anabolic mean? If catabolic is cutting, what's anabolic doing?
Building.
Yes, it's building. Okay, so anabolic reactions are building. A lot of people have heard about anabolic steroids, the naughty behaviors of people who take things to help themselves grow bigger than they are supposed to be able to. And sometimes you see women who look more like men and men who look like the Hulk, the Incredible Hulk, except they're not green. Anyway, bad idea. So oxidation reduction reactions. All right, so here we go. With oxidation reduction reactions, let's see if over here. All right, this isn't my favorite. All right, not my favorite. I'd rather be drawing, but let's say, okay, FAD and FADH2. Okay, so this is a vitamin. Okay, it's a flavin. Okay, so this is one of our carriers. You'll need to know that the FADH2 and NADH are our coenzymes. They're vitamins whose job is to act as energy carriers, okay? From when we are breaking down our glucose, Every time something comes off, we're going to send the energy packet off, headed towards the mitochondria, okay? But what's happening is something called a redox reaction. So we say that the molecule that has lost an electron, lost something that is energy, is oxidized. The one who gained that electron is said to be reduced. So they call them redox. So see the RED from reduced, ox for oxidized. You must have a pairing to do this. This is where, let's say that I have a very hot, stinky potato, and I throw it to Beth. Okay, so Beth now caught the hot, stinky potato. I have just been oxidized. You just got a nice, hot, stinky potato. It's worth energy, okay, because it's hot. It's stinky. Sorry. So you've been reduced because it was stinky, but you've been energized because it was hot. You with me? Okay, so a redox reaction always has to have a pairing where you've got one that is giving off something, the electron, and a proton will come with it because we don't have naked electrons. That's just not cool. So we then reduce something else. The reduced molecule is now carrying energy. It has more energy. Okay, we good? Yes? Okay. All right. So all of these redox reactions of ours are catalyzed by enzymes. Okay, we've got these different ACEs, dehydrogenases, oxidases. Okay, so if you catch an electron and a proton, you are now reduced. And that's why you'll see it's NAD picks up an H, FAD picks up another H. So that's what those things are doing. Everybody okay so far? Okay, carrying on. Now, ATP synthesis. There are two different ways to synthesize ATP in general, okay? There's substrate level phosphorylation and there's oxidative phosphorylation. Substrate level phosphorylation you have actually met because you met it in the muscles, okay? There is this stuff called creatine phosphate. And this is one of those where I say, well, Thais, there's somebody who, if I don't pay them back their $20, they're going to break my knees. And I just happened to see that you had $20. So would you mind lending me $20? I promise I will pay you back on Tuesday next week. I promise. And so Thais, because she would not want me to have my knees broken just for a lousy $20, and there's no elective surgeries right now, so I would have to limp around on broken knees for who knows how long until COVID is gone. So anyway, so she gives me the $20. I then am re-energized with my $20. I'm okay. I get to keep going on. Meanwhile, poor Thais, she's short her $20. But luckily, what will happen is something called substrate level phosphorylation, where she's going to get some again. So substrate level phosphorylation is really where what we do is borrow from Peter to pay Paul, and then we recharge Peter. Okay, we good? Does this make sense? So it's catalyzed by this enzyme. So in your books, these pictures are over on page 936. Okay. So all we do is we have an enzyme that is going to bring ADP, which is ATP minus one of its high energy phosphate bonds, and add a high energy phosphate group to it. Okay, so we just recharged the ADP, turned it into ATP again by borrowing it from, well, we actually stole it, but somebody else is going to repay it. We know for sure that they'll get repaid. Okay, so it doesn't require the mitochondria. This can happen absolutely anywhere in the cell. All right. Then the next step, the other flavor, is oxidative phosphorylation. Oxidative means that we are going to use the electron transport chain. We only do this in the mitochondria. And if you remember the way the mitochondria was set up, remember they were kind of these bean-shaped things, and inside that they had these woven, it was like a woven chamber. It had this weird sectioning they were called cristae. Remember that? Does that ring a bell? If it does not, you need to go back to the cell chapter and take a look at mitochondria, okay? So they look like these kind of beans. That's cool, Beth. All right, so they look like these beans with this waffling inside, right? Well, what those cristae do is they really create two separate compartments inside the mitochondria. And we use that to create a battery. I don't know if y'all have ever looked inside like a car battery. And to be honest, I haven't looked in one lately because now cars are just great big computers and they're really beyond me. But in the old day, you could look inside and you'd see all these chambers and you had to keep water in all these chambers. You know, this was back after the horse and chariot days, you know, but back when I was young, God was young, and way back then. But all those chambers, and that's how we're separating charge. And you know that if you were to hold the red terminal and the black terminal with your bare hands, that you would then have current flow through you because you would then have those two chambers connected. Does that make sense? Right? Okay. That would be really bad. You would probably die. But in this case, what we have is this cristae, this membrane inside the mitochondrion. And we have these pumps, they're proton pumps. And what they're doing is they're creating a battery, really. And those NADH and FADH2 are the taxis, and they're bringing the electrons and protons that we pump through these pumps to separate the charges. And then we have at the end of all of this, there's this enzyme that's called ATP synthase. And ATP synthase takes ADP and puts that high energy phosphate bond on there and creates ATP. But the other thing that happens is that proton, when it shoots through, is going to hook up with oxygen. This is oxidative phosphorylation. We're going to actually create ATP and water. You make water. You're amazing. I think making water is more important than being able to make wine. I think that's a bigger thing to put on your CV, right? Okay. So anyway, so oxidative phosphorylation requires the mitochondria, and it requires the electron transport chain. All right. All right. So now, whoops, right there. In your books over on page 937 is kind of this summary page. What I want you to notice is color themes. Okay. Glycolysis is always going to be kind of this apricot-y color or peach. Then the Krebs cycle or citric acid cycle is the green. It will always be green. And then the electron transport will always be plum. Okay, hold on to those because as we go through here, these are the steps in order to take glucose, C6H12O6, and turn it all the way into 6 carbon dioxides, 6 waters, and a whole bunch of ATPs. Okay. Good. Okay, so we're going to start with glycolysis. So when we look at carbohydrate metabolism, because that's what we're starting with, we're doing glucose, then we'll add in the other nutrients in a bit. Okay, so carbohydrate metabolism, the summary of all of this is on, let's see, they show that expression at the bottom of page 937. I want you to know this one. C6H12O6 is the chemical formula for glucose. That's our monomer unit that we use in making energy. Okay, it's how we build glycogen and it's what we clip off of glycogen. So C6H12O6 plus 6 O2, so 6 oxygen molecules, will become, through the process of this oxidative phosphorylation, it's going to become 6 H2O molecules, 6 carbon dioxide molecules, and a bunch of ATPs, 32, 36. It depends on how efficient we are. ATPs, a lot, okay? If we do not have oxygen, And we do not have anybody to accept those protons that go shooting through when we're using that ATP synthase in the mitochondrion. We will only make a couple of ATPs. We will die. Without our mitochondria working, we die. Okay? All right. So on that happy note, moving along. Okay, when we look at glycolysis, what you're looking at on page 938, there are steps to this. All right. So I don't know how well you can see my tiny little self here, but I think of the glucose molecule has 6 carbons, right? So if I say, well, I've got 6, so I've got my 6 fingers, right? And so first thing that you have to do when you're looking at this, the very top box, you'll see that I had to invest 2 ATPs. Do you see that? So the reason I had to do that is because I had to kind of destabilize the molecule. So you had to invest in order to get this thing going. It's kind of like kick-starting it. So I had to invest a little something, 2 ATPs. So now I'm unstable and the molecule breaks apart into 2 3-carbon units. Okay, so as we go through this, here one moment, please. So we've added our 2 ATPs and we've turned it into 2 3-carbon units. I am so not interested in your knowing the names of these 2 because they keep going back and forth, but there are 2 3-carbon units, each with a little phosphate attached to them now, okay? So now these 2 3-carbon units from my original 6-carbon glucose are going to then go through a process where they're going to now lose that phosphate group. We're going to now create 4 ATPs. So now how many ATPs did we net? We put in 2. We came out with 4. So what's our gain? 2, right. So we've got 2 ATPs. That's lovely. Not very much, though, when we're looking for 32, 34, 36. Yeah, we're looking for a lot more. The other thing that happens is when these 3-carbon molecules become pyruvic acid, and we've got 2, right? Because pyruvic acid, 3-carbon unit, started with 6. So I've got 2 pyruvic acids. You also hear the term pyruvate. Pyruvic acid, pyruvate. Okay? Citric acid, citrate. All right. So 2 pyruvic acids. The other thing that happened is that 2 of these NADs were reduced. So I now have 2 taxis that are carrying energy. This energy is useless unless it finds its way to the mitochondria. So this glycolysis process happens anywhere in the cell. In the cytosol, it can happen anywhere. But we've only gotten a net of 2 ATPs, 2 in, 4 out, 2 net, unless this also gets to cash out. I tend to think of NADH and FADH2 as taxis that are actually carrying poker chips. I'm in the casino, and it's not a place you'll ever find me because but whatever. But you know, poker chips, could I take a poker chip that's a $5 poker chip and take it to the grocery store and say, here's my $5? Would they take that? No. Okay. That's because I have to take my $5 poker chip to the right place that's in the casino to cash out, correct? So the NADH and the FADH2 are carriers. And what they have is energy that has potential to make ATPs, but only if they get it to the mitochondria to cash out. Okay? So NADH and FADH2 are vitamins who are nothing more than transporters that get reduced to carry the energy to the mitochondria. All right.
So wait, you're saying the whole purpose of this little cycle is to create more NADH for later? And
these will be used. Well, it's all about making energy. It's all about making ATPs. It's all about making ATPs. So the 4 ATPs that we got out, Those are ATPs. We can use them now, okay? We just had to put in 2 to get out 4. We came ahead by 2.
Okay.
But
What's
these
the name
over,
of this called, by the way?
huh?
What is this like little part called?
This is called glycolysis. This whole
Glycolysis.
process. See the little bitty thing up here that says glycolysis?
Okay, so that's not the C6H12O6 then.
No, glucose is
Ah.
C6H12O6. Yes, that's glucose is the sugar. It's the monosaccharide. Glycolysis is the first lysis of glucose. It would
I
have
get
been
it.
nice if they'd said glucolysis instead of glycolysis, but you know, they like the Y instead of the U. All right? Makes sense? Whether it makes sense or not, does that make sense, whether you like the terminology or not?
It makes sense now, yes.
Okay, awesome. Okay, so we have been through glycolysis. What we have netted is 2 ATPs, and we have also reduced 2 NADHs, which are worth something, 4 to 6, 2 to 3 apiece of ATPs, depending on whether they get lost or they get there. It should be worth 3 ATPs apiece. If they get lost, then we have to start making averages, okay? So anyway, they're supposed to get into the mitochondria. Now, the next step down here. This little piece right here where we have, if we have oxygen, we go to the Krebs cycle. If we do not have oxygen, we don't get to go to the Krebs cycle. Here's the deal. We have already gotten our 4 ATPs. We've got our NADHs, but they ain't worth jack until we can get oxygen, because we have to have oxygen in order for this whole thing to work. It's why, you know, if somebody throttles you, you have no oxygen coming in, you die. Okay, we have to have oxygen. We are aerobic organisms. So what happens is, do you remember with muscles and muscle physiology, you know how that burn, like you can just, let's say that in the desperate need to get some exercise because all the gyms are closed and you can't use the Stairmaster. So you decide to go into the building and it has 5 floors and you go up and down and up and down and up and down the stairs, right? Until you can't go no more and you get to burn, right? Everybody had a muscle burn from just running too much or something? You know what I'm talking about at least? Okay.
Yes, feeling the burn.
Yeah, the burn. You feel the burn. So the burn is because of lactic acid buildup. And lactic acid is pyruvic acid that said, well, there's no oxygen. So once you've repaid your oxygen debt, in other words, you stop moving, you start breathing, and you get your oxygen back, then the lactic acid goes straight back to pyruvic acid. Okay? So when you are exercising, aerobic exercising means that you keep enough oxygen so you don't have to build up all that lactic acid. Okay? Whereas anaerobic exercise, where you're building up lactic acid, that's your burning stuff. Okay? All right, so now we go and say, well, I've stopped exercises. I'm breathing, I'm sitting, I'm chilling now. I'm sitting on my Pilates ball and bouncing, but that's not burning anything. Now I've got my 2 pyruvic acids. I got 2 3-carbon molecules. Now I go to my next stop, the Krebs cycle. Okay, so now the Krebs cycle, the green part. So now we're over on page 939. You realize we're working our way to 1,000. Page 1,000. We are going to go beyond that, so that's cool. Not today. All right, so my pyruvic acid comes in, and then what I want you to notice is, look at what happened. I lost a carbon dioxide from each one. Now they're showing 1 3-carbon unit, but how many did we have from our original C6H12O6 glucose? How many pyruvic acids did we get? 2. 2, yes, 2. Okay, thanks, Bob. So we got 2, and so each one of those now, I want you to hold on to this, because when we go around this cycle, which is almost like passing a hot potato, you end up, it's a truly well-cooked hot potato, and it falls apart and there's no potato left. Okay, by the time we're done, nothing of the original potato. So as I'm coming in here, my pyruvic acid, I get to go around this whole thing twice, because from 1 glucose, I had 2 pyruvates to go through here, okay? Now, pyruvic acid can't go through. It has to give up a carbon dioxide. It's too big, 3 carbons, not good. We want 2. What we want is an acetyl group is what it's called. 2 carbon units are called acetyl groups. Think back to what I said about the fatty acid chains. Those fatty acid chains are made up of a gajillion, well, that's a technical number, but anyway, gajillion. And you start looking at all your triglycerides, you've got a gajillion of these acetyl groups, because I think of acetyl groups as like, in Legos, the little blocks are just 2 little of the little nubby things. They're kind of like the basics. It might be part of, say, I don't know, a dinosaur, and then the kid can break it apart, and all of a sudden now it's part of a rocket ship, and we can break it down again, and we turn it into, I don't know, something to throw into the parents' feet because they've made you mad and they're walking around barefoot and you wanted to get even. I know, right? Who thinks of that stuff? Okay, so anyway. So if you think of acetyl groups as the basic Lego building blocks, it'll really take you far, because that is the coolest thing. This tiny little thing, this 2 carbon unit, it goes around the Krebs cycle and gives you a whole bunch of possible energy once we hook in with the electron transport chain in the mitochondria. The other thing is that I could say, oh, wait a minute, I don't want to burn this. I want to turn this into a piece of a castle. Okay, so we do magic, and guess where this happens? All hail the liver, right? So the liver does this magic stuff with all this. So, oh, I'm getting goosebumps. I am such a dweeb. All right. So anyway, so the carbon dioxide comes off, and every time a CO2 leaves, an NADH is formed. So I reduce an NAD. So I've got CO2 comes off. Now, how many times does this happen for one glucose molecule? Twice, right? Because I had 2 3 carbon units. So anyway, so I made 2 acetyl groups. So the acetyl group, when it comes in, now it can't come by itself. It has to have an escort. Its escort is called coenzyme A. So CoA is kind of like the, you know what, I tell you what, I'll get you in the door and then you're on your own. Okay, so CoA brings you in as an acetyl group and then drops you off. It says here, let's become a citric acid. And that's why they call this the citric acid cycle. Okay, so anyway, it goes all the way around here. Now, what happens as you're going around is a whole bunch of stuff. You absolutely, for this course, because it is not a biochemistry course, it's not even a biology course, you need the basics, but I'm not going to ask you to know that isocitrate and all this stuff, citrate to isocitrate to alpha ketoglutarate, none of that stuff, okay? But what I want you to get is the basics of what came off. You ready? We're going to start doing some add up maths. All right. So my acetyl group comes in, dropped off by CoA, who goes off and collects somebody else, another acetyl group who's coming in on the line. Maybe it's the other half of the glucose molecule from the original. Okay, so in comes the acetyl group. Acetyl group then comes in, it becomes citric acid, which then becomes isocitric acid. And then look what happened. A CO2 came off. Well, every time a CO2 comes off, then I'm going to reduce an NAD. I've got another taxi carrying potential energy. These are the poker chips. I'm going to cash out, right? By taking them to the electron transport chain. Hold on one moment, please. Look, another piece comes off. Then another NADH is formed. So all of a sudden already, look, here's one from one CO2. Here's another one from another CO2. Here's another. Uh-oh. Wait a minute. 1, 2, 3. I've lost the entire original molecule that came in. And yet still we go because we've started the machinery. So now we work our way around. Look at this over here. Do you see this where GDP is formed from GTP? So I took an ADP to ATP. You see that? That is called substrate level phosphorylation. I robbed Peter to pay Paul. Aha! So I made an ATP down here. Didn't need the electron transport chain for that, but this is happening in the mitochondria, and so I better have a mitochondria that works. Okay, so now I've made an ATP. Now, how many ATPs do I get from the Krebs cycle for one glucose molecule? 2, because I get 2 trips around the circle. Okay, good. So now I'm working my way along. I want to look over here. I've taken FADH and I have an FADH2 formed. And then I keep going, I get another NADH form. So as I go around this whole process, remember I got an when I started over here, right? If I kind of come back here, look at, I got 2 NADHs over here, right? From glycolysis. They're going off, hoping to find their way into the mitochondria to cash out their chips. I got those 2 ATPs. Then I get into here, and I've got 2 NADHs. I've got another 2, because remember, I got to do the math, right? Because I come through twice. So there's 4 NADHs, 6, 8, 10 NADHs from this original glucose molecule. You with me on this math? Okay. And then I also have FADH2s. Now, how many of those do I end up from my original glucose? 1 or 2? Fingers up. 2. Peace. All right. How many substrate level phosphorylation ATPs do I get from this? 2 here, plus I got 2 in glycolysis, didn't I? So I've got 4 ATPs that I earned. And then I've got all of this potential energy that I can cash out. But in order to do that, I have to go to the next place. You ready? Here we go. Turn your page. Okay. This is the electron transport chain. So in your books, on page 941 and 942, okay? This, I'm giving you the overview, and then I'm going to go backwards to the 941 page, okay? I want you to think of the electron transport chain. At least it helped me. You can think of it any way you want, but I'm just going to offer this up. If you think of it as like a pinball machine, okay? Now, I know most of you are way too young to have had the arcade things where you actually have one where you pull a plunger back and you let it go and the ball goes up and it goes ping, 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 ping as it's going down. But the principle is, right, you let a ball, you release it, it goes up, and then the higher up it goes and the more it hits, the more points you get, okay? If you've got somebody who gives it a real good pull back and whang, and it goes the most distance, you're going to get the most points. If you've got somebody who kind of does a half-hearted release, it only goes part way, you get fewer points. With me so far on the analogy? Okay, then. So here's the deal. NADH drops the proton-electron pairing at the very top of this cascade. It gets 3 ATPs worth of energy. FADH2 drops it farther down the chain. It gets fewer ATPs. It gets 2. So NAD is worth more than FAD. Okay? Just because of where we're dropping things off in this power me up chain. Okay? So back here on the previous page, 941, shows you what's kind of happening. Again, these cytochromes and all this stuff I'm not going to ask you about, but the principle is that I am pumping protons. And when I pump the protons from one chamber where all this Krebs cycle stuff is happening, and I pump the protons to another captured space, then what happens is I'm setting up a very unequal charge. And when you do that, that is how you will now create a current. And the way that it gets discharged is through this ATP synthase, okay? And this is a really lovely, huge picture in your books on page 941, okay? So what happens is once I have powered up everything, and by the way, they can actually see this stuff. How cool is that, right? Totally awesome. All right. But here is what's happening is that those protons, as they shoot through, they're actually making this thing turn like a turbine. And the protons shoot through the center. And when they come out, they are picked up by oxygen. Oxygen is the terminal electron acceptor for these protons. It makes water. You have to have oxygen to accept the protons. Water is formed, okay? Meanwhile, the energy that it represented has taken ADP and added a high energy phosphate bond to make ATP. Okay?
How come there's no oxygen in the picture? How come there's no O?
Why is there no O? I don't know why there's no O.
It just always bothers me. I like the pictures, but I like.
What O's here?
Okay. Just
Oh, okay. How about the O on page 2?
okay. That's better. But I like it. You said it needs it, and then it's not there, and it always
Oh,
confuses
how rude,
me.
right? Okay, gotcha.
Yeah. Sorry.
All right. It's kind of like we got the slide. Somebody's there to catch you. Not so much splat. Okay.
Yeah. Okay.
But it's really there. Okay. We better now?
Yes. Better.
Okay.
Thank
All right. Okay. You're no problem. Okay. So we've got this whole system now that helps us to make ATPs. Okay. So we're almost done. I just want to tie up the concept and then we'll move on to the next thing the next time on Thursday. Okay. So our energy yield, this particular put it all together thing is absolutely fabulous on 944. Put an asterisk by it. Look at this, because here's the deal. You need to understand the basics of this pretty much as just what I've covered, okay? So if it's not absolutely working for you, I mean, I think it seems like just from faces as I've peeked around and, you know, the finger thing, you're getting the basics of it, but make sure that you take a look at these pages and make sure you take a look at the links that are available, because there's some really good explaining. And, you know, I say it my way, it's the way I visualize it, but there are an awful lot of other ways. And sometimes when my way isn't the one, it's the next one that might click. Maybe I helped get you almost there, but not quite. And then it's like a song. That's what it took, is somebody on a guitar singing to me. All right, so we're going to summarize this and I'm going to release you from this and then we'll just have a chat. All right, so glycolysis, glucose to pyruvic acids. How many pyruvic acids do we get? 2, good. Okay, pyruvic acid. Through glycolysis, how many ATPs did we net? It's a magic number, 2. Yes, okay. And we made the NADH, which you can see has to travel and get into the mitochondria and find its way to the electron transport chain. It does not always, okay? Then once we have made our pyruvic acids, remember we have to ditch a carbon dioxide from each of the pyruvates in order to end up with our acetyl group, which has to hook up with CoA, coenzyme A. All that does is hook it into the Krebs cycle. That's it. Then it goes away and finds another acetyl group. It just makes this little cycle here. All right. Kind of like a Boy Scout on a never-ending loop to cross old ladies across the street, knowing the old lady's going to go into this bar and never come out again. Okay, so then we go into the Krebs cycle, and from the Krebs cycle, we have generated 2 ATPs by substrate level phosphorylation, okay? And we've generated all these NADHs plus the FADH2. So we've got 6 NADHs. Each of those will be worth 3 ATPs, 2 FADH2s, which each of which easy for me to say, is worth 2. And as long as we get to cash out at the electron transport chain, okay? So once you've put all this stuff together, you can see that my entire flow of this stuff it's going to give me a whole lot of ATPs. And in the end, if I count absolutely everything together and everybody made it to the electron transport chain, I can get about 36 to 38 ATPs from one glucose molecule. Okay, that's a big deal, and it's kind of cool, isn't it? Okay, all right. So that's the end of what we need to do for today, and then we'll, I think, well, let's see. The last little bits. Would you be willing to just do a couple terms and then we'll finish? Would that be all right? We've had them already, so I just wanted to quick do them. All right, glycogenesis. What do you think I'm doing? It should be glycogenesis, but that sounds like you have a stutter. What am I doing?
Creating
Creating glycogen, creating glycogen, right?
Dang it. I was on mute. I was saying it.
Oh, you were, okay, and I couldn't see your lips because you're in and out of your
I know. Somebody's got to be here.
I know, it's okay. Hi there. Oh, lap sitter. All right, so glycogenesis. If I have extra energy, I can make glycogen. It's the first thing I do. I make the cache for my pocket in my underwear drawer, okay? So glycogenesis is generating glycogen from glucose. Cool? Okay. Glycogenolysis. What do you think I'm doing?
breaking down the glycogen.
I'm breaking down the glycogen. So if I've got lots of energy, I've got enough ITPs, I'm going to do glycogenesis. I'm going to have insulin. It's going to help me do it, right? It's going to get that stuff into the cells. Glycogenolysis is where my glucagon comes on. I talk to my liver, I talk to my skeletal muscle, but primarily my liver. And I'm going to say, hey, you know, all that glycogen you stored, I want that back. Break it down. Okay, so glycogenolysis, break it down into glucose. It's why we carbo load. So we have that cache in our pocket, big wads of cache in our pocket. And then gluconeogenesis. What am I doing?
Neo.
New glucose.
I'm making new glucose.
From,
Yeah.
from non-carbohydrate molecule, we're doing glucose.
Yeah, you're making glucose
From
from
non-carbs.
from amino acids and from the glycerol. That's that backbone of our lipids. So if I take the glycerol backbone or I take amino acids and I turn them into an aspect of glucose, it may be acetyl groups. But anyway, if I do that, that is gluconeogenesis. That's what the glucagon, there's way too many glucose words, right? Glyco, whatever. But anyway, gluconeogenesis is where glucagon, made by our alpha cells in our pancreas, go to the liver and say, hey, you know what? We've run out of our carbs. We've run out of our fats. It's time to start breaking other stuff down. Okay, cool? All right. So when we meet again on Thursday,